Say hello, Matilda. Say hello. People were asking me about Matilda, and she likes to help me out. So I thought like she would have a visit. She'd help me teach the lesson, okay? What do you think? Good idea? No? Matilda, you see yourself on the camera? Wave your paw. Hello. Okay, say goodbye. All right, bye. So take off. All right. Okay, that was fun. I'm going to start off with a golf joke because, it's that season. For all you golfers out there, you're all getting excited, aren't you? Why did the golfer play with the wood? Why did he choose a wood? Because he was suffering from iron deficiency. Yeah, not funny. Golf, you have woods and irons, and I thought it was funny. See, the good thing about doing a video is you can't throw anything at me. I wanted to show you one thing more to help explain some stuff. An example, I showed you how in one of the videos that hydrogen combines. Let me show you again. And hopefully this is going to make some sense and help you in this next lesson. Can you see that hydrogen has its electron? Does that show up? Let's turn this. That's more better. And then it combines with an adjacent hydrogen atoms, and then the electrons approach each other and it creates this bond. Note that the 1s orbital now has one of its own electrons, and because it's sharing his neighbors, it's got a 1s2 configuration, which is very stable for both atoms, and that is the basis for a covalent bond. Let me show you one more. Carbon. Do you remember carbon? It's got atomic number 6, and it's got, here's its 1s2, 2s2, 2p2. That's its electron configuration. And the Bohr model would be this. Here's the 1s2, first energy level, and then the 4 electrons in the second energy level. 1, 2, 3, 4. And this is the Bohr model of carbon. And what happens is here's a hydrogen here, and a hydrogen here, and a hydrogen here, and a 4th hydrogen here, and it can combine. They can share at these particular locations, and note what happens. This hydrogen is now sharing an electron, so he's happy. He's 1s2, and he's 1s2, very stable, 1s2, 1s2. All the hydrogens are satisfied because their orbitals are filled up, but the carbon is now sharing 1, 2, 3, 4 more electrons, which adds to these 4 here in the s and the p orbitals. Now the p orbitals is filled up at 6, and what's 4 plus 2 plus 2? 4 plus 2 plus 2 is 8. That's that magic octet number. And this is the basis for carbon, methane gas, CH4. This is how CH4 forms, which is the most basic organic molecule. It all fits together, see? And you might be wondering, well, where do these 4 hydrogens come from? They're everywhere. There's millions and billions and billions and billions of these atoms, so don't worry about that. This is the most basic organic molecule, CH4, and this is exactly how it forms. Look at that. I'm going to come back to that again, as you'll see, but I just wanted to show you that. To help you really, really understand this, Professor G.N. Lewis created this concept called and they named them Lewis electron dot structures. Now, Professor Lewis, the GN, is Gilbert Newton Lewis. Gilbert Newton. I think Gilbert. I don't have a problem with Gilbert, but apparently he did, so he went by GN. Because Newton Newton's a great name. After all, it's a perfectly valid cookie when you combine it with the figs, the fig jam. I don't like fig Newtons, but a lot of people do. Anyway, Lewis structures. Let me show you how a Lewis structure works, and it's going to be the topic of our next couple discussions and assignments. The basic format for a Lewis structure is we put a symbol of an element, let's just pick element X, and we write a dot representing all valence electrons. Which leads me to a general question. What's the difference between an electron in a hydrogen atom and the electrons in a chlorine atom? There's no difference. They're the same. An electron is an electron. The only difference is one has 1 and the other one has 7 valence electrons. Okay, just saying. I had to get that off my chest. All right, so anyway, here's element X. Could be anything. Could be carbon, could be hydrogen, could be an element with 2 symbols like Ne, which is neon. We write 1 dot for 1 valence electron. And then here, let me say it again. The element, imagine it inside an invisible box with 4 sides, square, and this square represents that s orbital, and the 3 p's representing the valence electrons in the outer energy level, s and 1s and 3 p's, which can accommodate a total of 6 electrons, if you remember from whatever we were talking about. So we can put 2 electrons here, 2 there, 2 there, 2 there. So this is how we write them. We put a dot. Now, according to the Hund rule, which I never went over, they fill up. They fill up like this. 1 goes here, the second one goes here, the third one goes there, the fourth one goes there. That's 4. But what if there's 5 valence electrons? Then it goes like this, and it's in alignment, parallel to this invisible square. And here's the 6th valence electron, the 7th, and the 8th valence electron. We would never draw it like this. That's bad form. See, like that? No, it's not like that. We draw an individual Lewis structure like that. So what's neon's Lewis structure? Well, if you check your periodic table, neon is a noble gas in group 18. They all have 8 valence electrons, and so neon would look like this. See that? Here, let me show you a couple. Here, let's pick one randomly. What would boron look like? Boron has 3 valence electrons. 1, 2, 3. See how simple that is? This is all in the textbook, by the way. You can look it up. And what about nitrogen? That's got 5. That's a little tricky. 1, 2, 3, 4, 5. See that? Now you might say, well, can I put the 2 here, or can I put the pair there? Doesn't matter where you put them. You could put the pair down there. I'm just saying for demonstration purposes, because these electrons are moving. They're in a pair, and these are all single, and that's 1, 2, 3, 4, 5. That's how we draw Lewis structures. Easy, right? Very easy. Let me show you how these combine. Now you're going to need a periodic table to do all this stuff. Now there's one in the textbook. It's hard to access online because it's all the way in the back, or it's in chapter 4. So you might want to go on the internet, and you can look on the internet. There's plenty of periodic tables on the internet. And you can make a copy of one and use it, work with it. Doesn't that sound like fun? It is fun if you are, really into this. It's fun. I think it's fun. Okay, it's not fun. Just be happy I'm not testing you. Well, anyway, let's do a simple, let's go back to the methane molecule. Remember I drew that it was CH4. Let me show you how to do it with a Lewis structure. Okay, I'm going to use different colors for demonstration purposes. So what do? let's draw the carbon atom's Lewis structure. There are 4 valence electrons. Here's carbon. 1, 2, 3, 4. All these have 4, including carbon. So we write the 4 dots like that. 1, 2, 3, 4. See? You know? And there's 4 hydrogens. Well, let's show them. 1. Use a different color. Red. Choose red. 2, 3, 4. Right? Look what happens. This one combines over here. This one is going to combine over here. This one's going to combine over there. And the 4th one's going to combine over there. If I bring it all together, the Lewis structure would look like this. Here's the carbon. I got 1, 2, 3, 4 electrons. And then I have the 4 hydrogen atoms. 1, 2, 3, 4. And this here, this here, this here, this here. 1 electron here in the pair comes from the hydrogen, 1 comes from the carbon, 1 comes from the hydrogen, and all the way around. That is the Lewis structure for methane. And we can write, instead of writing all these dots, we can put a dashed line. Maybe you've seen carbon and 4 hydrogens written like this. See the dash, 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 and a hydrogen here. This is called a structural formula for CH4. That's a structural formula there. And each one of those dashes, which you've seen, that's how we write molecules, really represents 2 valence electrons. Now you know. You might not have known that before, but you know it now. So I'm going to ask you to try to do some easy problems. I'm going to do the first one. We'll use the textbook for now. I was going to make up some problems. Oh, by the way, if you're submitting this on a Google Doc, you can use the scribble marker to draw out the Lewis structures, because it might be hard to type that in. See, I told you it was going to be fun. There's some practice problems, guys, in our textbook on page 202. 1 and 2, there's several of them there. I'm going to do the first one. On page 202, practice problems 1 and 2. 1 has 4 parts, and 2 is 1 part. So it says H2S, whatever that is. H2S. What's the Lewis structure for H2S? Well, here's the Lewis structure for H. Here's a second H. And sulfur on the periodic table, because that's what the S is, has 6 valence electrons. See, they all have 6 valence electrons. So how do we draw the 6 electrons for sulfur? Like this. 1, 2, 3, 4, 5, 6. So we already have these orbitals filled up here. But these orbitals are missing an electron. So this is a perfect place for hydrogen to hook in. And this hydrogen combined there. So the Lewis structure, when you bring everything together, would look like this. Sulfur with its 2 electrons here and its 2 electrons there, and 1 there and 1 there. And here's hydrogen here and hydrogen there. And here is hydrogen's electron. And here's hydrogen's electron. And this is the Lewis structure. See how easy that is? And you can also write it like this. S with a dash line H and a dash line H. And you can put the unpaired electron, the unshared electrons there. And you could write this like that. I would accept that on the test, either one. Now, when you're really good at this, we don't even put these electrons here because we know they're there. Chemists know they're there. We just would write S, H, H. And this is a bent molecule. You'll notice that. There's a reason why it's bent. So anyway, that's my thing. Look for the assignment, and I'm out of time. Bye.